Okay, so we're going to finish up molecular orbital theory with these last two questions. We kind of already answered this one last time, but the difference here is pentadiene. That's where people tend to get confused. So let me draw this out. We have cyclopentadiene, and we have 1, 3. It doesn't matter where you start numbering. 1, 3. Okay, so we're going essentially energy transition. We're talking about exciting it, right? And so when we go from the ground to the excited state of like the other molecules that we did, what was the most favorable jump? Where did we always move an electron when we got excited? And then someone, while you guys are telling me that, ask what handout this is. So this is the new chapter 13 handout. It's on Canvas. Okay, so we got two different answers. Awesome. So one person said pi 2 to pi 3, and someone said HOMO to LUMO. So I'm going to say HOMO to LUMO is always like the right way to go about it, right? But if he asks you for like the pi number, we then have to think how many double bonds are there? There's 2. This is not a plus, minus, or radical, so it's not a p. So we have 1, 2, 3, 4 energy levels. I'm going a little bit fast because we did this last time, but if you have any questions, please don't be shy. Let me know. So again, we make 1 energy level for each of these orbitals. And we know that we have 1, 2, 3, 4 electrons. And so the highest number with an electron in it is our HOMO. And the lowest empty one is our LUMO. So as you told me, we're going to jump from HOMO to LUMO. And so I don't remember who said it, but whoever said pi 2 to pi 3 was correct. So our most favorable is from pi 2 to pi 3 star. So just kind of don't always assume it's pi 2 to pi 3. Make sure the numbers match up. But this is how you do it in all of the examples. So someone asked, orbitals are for double bonds only. So in molecular orbital theory, we're going to draw an orbital for double bonds, positive charges, negative charges, and radicals. And so I made this handy dandy little note here. You guys want to write it down? And so all of those are going to count towards molecular orbital theory. And then someone asked, so essentially they're asking for energy levels. Yes, so they're basically asking you where the electron is going to go from and where it's going to. And we're going to go from one of the pi to another pi. Alrighty. So I'll give this another second for people to write down. And then we can go on to the last question for this section. And while I leave this up, pretty please sign the attendance at some points before you leave. All right, so I'm going to close this back up. And the next question is, which of the molecules on UV absorption and longest wavelength? So we know that if we're talking about UV absorption, which type of spectroscopy are we using? And then someone asked a question, and I am not ignoring you. I'm just going to go back to it after we finish this example. So yeah, when we have UV absorption, we know we're talking about UV vis spec. And in UV vis spec, longer wavelength, is that more conjugated or less conjugated?
Conjugated.
More conjugated. Awesome. So we're looking for most conjugated. All right. So which one of these is not even conjugated at all? Yes, exactly. So this one is not conjugated at all because we have one double bond here and one over here. This is actually isolated. All right. So here we have double bond, single bond, double bond, single bond, double bond. So how many double bonds do we have in conjugation? I'll actually highlight it for you guys. That's easier. Double, single, double, single, double. So we have 3 double bonds in conjugation. I agree. For the second one, double, single, double, single. And our other double bond is all the way over here. So we only have 2 in conjugation. Double, single, double, single. No double bond. It's all the way over here. So this is again only 2 in conjugation. This last one, 2, 1, 2, 1. Again, only 2 double bonds in conjugation. So which one of these is going to have the longest wavelength on UV spectroscopy? Number 1, I agree. So I'm going to put a circle and a star. So any questions about how I went about this one? Someone asked, how do you check the number of conjugated double bonds? So remember, conjugation is when you have a double bond followed by a single bond and then another double bond. So we're looking for this kind of configuration. So double, single, double, single. So double, single, double, single, double. All right, so while I give you guys a second to look at that, I'm going to go back to the question that someone asked about the last example. So I'm just going to scroll up a little bit. So the question was, okay, this is a really good question. They said, so is this molecular energy structure similar to 1,3-butadiene? Yes, exactly. So I love that you pointed that out because you guys have to notice that no matter how many carbons there are, whether this is cyclic or not, we have 2 double bonds, and it's the same for 1,3-butadiene. So they're essentially, for the purposes of this class, going to have the same energy configuration because it's still just, oopsie, sorry about that. It's still just 2 double bonds. So yes, they are pretty much the same. And yes, so for this one, it would be 2 double bonds in conjugation. If we had this, it would be 4. But let's say we had something like 1, 2, 3. So here, how many double bonds do we have in conjugation? Yes, exactly. So it'd still be 2 because this one is more than 1 single bond away. These 2 carbons are in the way. So it's actually not going to be conjugated. So there is conjugation here, but only 2 of the 3 double bonds are in that conjugated system. Okay, I hope that makes sense. Okay, got it. Yay! All right. So we're going to start something a little bit different, and we're going to do another reaction. So this one is actually super, super straightforward. That doesn't mean it's easy, but, you know, I think we have a pretty good shot at getting through this. So we did something very similar to this in organic, why did I say it like that? In Orgo 1. So in Orgo 1, we did 1 double bond reacting with HBr. But now it's a little bit different because we have to decide which of these two double bonds are going to react, right? So something we talked about last chapter or earlier this chapter is stability of double bonds. So let's say this is number 1 and this is number 2. Which double bond is going to be less stable? Number 2. And why is that? What do we think? So what makes a double bond? Yes. Okay, awesome. So it has more substituents on. So this double bond has 1, 2. This double bond has 1, 2. So this one is spread out, whereas this one is on one side. And so I would agree that this one is more reactive. And also, this one has less steric hindrance on this side, so it's more able to react. So, yes. All right, so now that we know number 2 is going to react. Okay, so someone asked, so is number 2 more stable? No, so number 2 is going to be less stable. This is the less stable one because, so this is kind of in his PowerPoint slides. It gives you like the order of stability of all the different kinds of double bonds. But we know it's going to be more stable if we have a substituent on either side than if we have 2 substituents on one side because of steric hindrance and things like that. Also, this side is open. It's not sterically hindered, so it's going to be easier to attack. So that's why we're going to say this one is less stable and more reactive. All right, so it's going to attack here, and bromine gets the electrons. So I'm going to add a page to draw the intermediate here. All right, so we know it attacks, takes the hydrogen, and which side of the double bond are we going to add the hydrogen to, A or B? And someone made a really good point. The double bond is acting like a nucleophile. That's correct, because it's using its electrons to attack the hydrogen. I totally agree. And so once it attacks, someone said that it will add a hydrogen to B, and I also agree, because we're going to want to add hydrogens to the side that already has the most hydrogens, and we end up getting a plus charge here. And then someone said, would I explain that again? I just saw that message, so I don't know which part you're talking about, but let me know and I will definitely explain it again. Okay, in the meantime, now we have Br minus, and it's going to go ahead and attack the positive charge because it's negative. It wants to attack the positive and make something neutral. So we end up getting HBr. And so, okay, as far as the double bond part, I just want you guys to think of it as this one is more balanced. There's one carbon on each side, one substituent, I guess, on each side. And for the other one, it has 2 things on one side, which is not great, sterically speaking, and also the other side is empty. So we're able to use these electrons as a nucleophile and it has less hindrance than this one, because this one's trapped in a ring, this one's out in the open. That's how you can think about it. All right, so this was one direction the path could have taken, but at this point, what's something we can do with plus charges to move them around? I will accept 2 answers. Wow, you guys got it right off the bat. So resonance and delocalization, yes. Okay, so the other thing you could have said is a rearrangement. So this is not exactly a rearrangement, but we have done that in the past. But in this example, I'll do in red the alternate pathway. We could have brought these electrons here, and we would have gotten the hydrogen doesn't move because it's already been bound to the carbon. Now we have our double bond here. And so that means our new plus charge is here. So if we did that, at this point, the bromine could have come in and attacked the plus charge, and we would have gotten I'm sorry, my screen keeps like freaking out. I don't know why it does that, but it'd be like that, I guess. Ta-da! Okay, so at this point, we have to compare and start over. At this point, we have to compare and contrast these two, right? And so we know that the H and the Br are adjacent to one another here, and over here we did resonance, so they're kind of far apart. So how we go about naming this is, let me zoom in. Wherever the hydrogen added, we're going to call that 1. And we're going to start counting from there. So 1, 2. So we call this the 1, 2 product. And then someone asked why I called it 1. So wherever we start the hydrogen, or excuse me, wherever we added the hydrogen, that's where we start counting. So we're going to count 1. And this is not the same as like IUPAC counting. This is just for figuring out what the product is. So when we're talking about the 1, 2 product, we mean that it's 1, 2. That's their relationship to one another. Whereas here, if we start again, number 1 is where we added the hydrogen, number 2, number 3, number 4. So this is actually the 1, 4 product. I know the numbering thing can be a little bit weird, but does this sort of kind of make sense? I got it, I think so. Perfect, I love to see it. Okay, so any questions on this mechanism in and of itself? Okay, I'll leave it up for another second and then we'll scroll back up and answer the questions on the handout. And yes, the least stable bond is going to be the one that attacks. And it will be pretty obvious or clear to you which one that's supposed to be. Like, okay, so someone else asked, just to be sure, the reason we picked the outside double bond is because it's not in the ring. So yeah, you can think of it like that. So this one is stuck in the ring, we can say. This one is outside, and so that's why it's able to attack. Alrighty, so I'm going to scroll up here and let's answer these questions. So I'm going to ask you the question and you tell me A, B, C, or D, what is what. So which one of these is the nucleophile? Yes, I absolutely agree. We're going to say A. Which one is the electrophile? B. I think so too. Because remember, the nucleophile is what does the attacking. The electrophile is what is being attacked. So I agree, B was attacked. Which one is the 1,2 product? D, I agree. So we'll say 1,2. And then which one is the 1,4 product? I agree. Super. All right, so we haven't talked about kinetic and thermodynamic yet, but I'm going to zoom out. And actually, I'm going to move this up here so that if you... just kidding, it's not going to fit. All right, I will let you guys take a picture of both at the end. But now we're going to talk about kinetic and thermodynamics. So we're going to scroll down once again, and I'm going to make a lovely little divider. That's not even, that's going to bother me. Okay, so we have our kinetic and thermodynamic products. And by the name, you can probably predict some things about it, but let's start with kinetic. So the kinetic product is going to be the one that forms the fastest. But we do have to put a little asterisk there. And we're going to say not at equilibrium, aka at low temps. So at low temperatures, the kinetic product forms the fastest. And the reason for that is because the kinetic product has the lowest activation energy. And I'll actually write this out for you guys. The thermodynamic product is going to form the fastest, actually, yeah, only at high temps, aka at equilibrium. And the reason for that is it has the lowest potential energy. The reason it has the lowest potential energy is because it is the most stable product. Sorry, I had to move it around a little bit at the end. And just to make it kind of look the same, I'll change this around a tad. I feel like I made it more complicated than it needed to be. So kinetic product has the lowest activation energy. Thermodynamic product has the lowest potential energy. And something I want to make sure you guys know is we're always going to talk in terms of lowest. A lot of people will start saying, okay, then thermodynamic has the highest activation energy and kinetic has the highest potential energy. No, we don't think about it like that. The thermodynamic and the kinetic product can be the same sometimes, right? So we only think in terms of lowest and lowest. Any questions on just this conceptual definition that I gave you? Questions, comments, concerns? Any such thing? All right, so in that case, let's go up here. And I want you guys to take a second and look at this. And with the definitions I gave you for thermodynamic and kinetic, I want you to think about which one of these is which. And so I'm going to give you approximately a minute to go ahead and do that. I unpaused the recording. So now that you guys have had a minute to think about it and I've seen what you guys have said, let's go ahead and talk about it. So a couple people said that C is the thermodynamic product, and we said that, I believe, yeah, okay. So 1-4 is C, and 1-2 is D. So you guys said that C is the thermodynamic. Why do you think so? Does someone want to explain? Aha! You guys are too good. You know all my tricks. So it has the more stable product, and how do we know which one is more stable? Because this one has the most stable double bond. This double bond only has 2 substituents. This one has 3. So this is actually going to be the most stable product. So we can say this is the thermodynamic product. And so that doesn't necessarily mean that D has to be kinetic, but that's what you guys said. So does anyone want to tell me why they think D is kinetic? Sorry, very sleepy today. Anyone want to take a guess? Oh, okay. This is the answer I thought I was going to get. So someone said they don't know how to tell without knowing the other one is thermodynamic. So that's what a lot of people do. They say one of them is thermodynamic, and then they have to figure out, oh, I guess the other one's kinetic. But you can't always count on that, right? So, okay, so someone said they just remember 1-2 is kinetic and 1-4 is thermodynamic. That's not the best way to go about it. And I know that that's what people will recommend because that's just like, easy. That's what you get from the book. But I have a better way. Okay, let's look at the rosemary method for doing this. So the thermodynamic product, you guys had a perfect reasoning for it. You said that the double bond is more stable, more substituted. Therefore, this has to be thermodynamic, right? And I actually agree that this one is kinetic, but the reason it's kinetic is because it's formed like directly, right? So this step for doing resonance takes a lot of energy, right? And so the energy that it takes to get from point A to point B is a lot smaller than it takes to go from here to here to here. So that's why this is kinetic, because it has a lower activation energy. And then someone said, how do you know how much energy is being used relatively? And this person had also said, like, don't you need like data to know which is which? Yes, but at the same time, look, if you see that this one reacts, you make the cation, you directly attack the cation, and you get your final answer, right? Whereas for the second one, you attack, get the cation, do resonance. Once you do resonance, you have a new carbocation, and if you'll notice, this is a tertiary, this is a secondary. So the secondary is less stable, so that's another aspect for it. And then here, finally, you attack and you get the product. So this one takes a lot less energy because it takes a lot less steps. And then someone apologized for like joining and leaving because WebEx is having issues. Do not worry about it. WebEx is super annoying. And someone else said they kept having issues. I hope that the recording doesn't have the same issues. I don't know. Because other people were saying they weren't hearing it. So I think it might just be like your end. I'm not sure. I'll watch the recording back just to see if it's still having the issues. And if it's on my end, I'll contact like the tech support people and see what I can do about it. Okay, and then someone who was asking about the Kinetic and Thermodynamic Product said it's starting to make more sense. So I'm going to go ahead and write kinetic. And I'll give you a second to look at it, think about it, screenshot it, write it down, whatever you want to do. And let me know if you have any questions, comments, concerns, anything at all. So the last thing that I wanted to do today is the energy diagram. So someone was saying, like, don't you need data to figure it out? So this is pretty much the data they would give you. It's the reaction coordination diagram. There we go. The reaction coordination diagram is essentially telling us this is time. So like it's like the how long the reaction takes. But we modified it a little bit because our starting material is here and A and B are our products. So let's zoom in just a tad more. Okay, at this point, we're not thinking 1, 2, 1, 4. We're just thinking about this diagram. So don't connect it to what we just did. Think of it as a completely separate thing for this moment, right? So at this moment, we know this is our starting material, right? And we can go to our two different products. How do we know the activation energy? Like from this, how could we tell what the activation energy is? Yes, so it's the peak on the hill. And I know someone else asked the question. I will get to it. I just want to get through this point first, and then we'll go back to it. So you are absolutely right. So this part up here is the activation energy. And so what is this down here? So we know A and B are our products. So what's this line at the end? So right here and right here is what I mean. In the middle is just like our starting material. So that's like the energy of our starting material. And yes.
Is it the transition state?
I'm sorry, what was it you said?
Is it the transition state?
So the transition state, good guess, but the transition state is going to be here. So the stability of our transition state is actually going to tell us about the activation energy. The line down here, someone mentioned in the chat, is actually our potential energy, because this is the energy of our product, right? Because this is energy. So this line right here is basically telling us how much energy our product has. Same with right here. So now that we have those two things defined, we can go in and figure out which one is kinetic and which one is thermodynamic. So how do we tell if something is kinetic? What are we looking for? And you can just tell me higher or lower, and then activation energy or potential energy. Oh yeah, so everyone said lowest activation energy. I agree. So A or B, which one has the lowest activation energy? A, awesome. So we know that A is our kinetic. Actually, yeah, whatever. A is our kinetic product. Sweet. All right, so now how do we tell? You know what, I'll write it up here just so there's some, whatever. I hope you guys can figure out that it goes with A. All right, so how do we tell whether something is a thermodynamic product? Highest, lowest, activation, or potential? One person gave me an answer, but I'm waiting for a couple more. Okay, so before we go on, someone said, but don't these products go through different mechanisms? Oh my goodness. Take two. Someone asked, but wouldn't those products go by different mechanisms? So wouldn't they have different energy diagrams? So normally, yeah, each product could have its own energy diagram, but in reactions like this one, where we have, like, for example, the 1214 product, we can plot it in a certain way that can show us the two reactions, like, compared to one another. So you can start with the product in the middle and you can compare one answer to the other answer. So usually you guys are used to seeing each reaction having its own, but we can manipulate the energy diagrams to show us both products at the same time, if that makes sense. Okay, so a couple people told me that lowest potential energy equals thermodynamic. So which one is our thermodynamic, A or B? A, how spicy of me, right? So in this example, the kinetic product and the thermodynamic product are both A. So wink, wink, nudge, nudge. You should know this one because Dr. West may or may not like this graph. Wink, wink, nudge, nudge. And don't ever assume that just because, like, A is kinetic, we could have just said B is thermodynamic, right? Because that's what students are kind of used to doing. And no shade, I used to do the exact same thing until someone explained it to me. So again, always look at lowest activation energy and lowest potential energy. All right. The other thing I want to mention, I'm going to make a little note here. So equilibrium, aka under thermodynamic control, aka reversible. All mean the same thing. So if he tells you any of these three things, equilibrium, thermodynamic control, reversible, all of those just mean the most stable product will form the fastest. So if he gives you any kind of question and he says, which product is formed fastest under equilibrium or under thermodynamic control or in a reversible reaction, the answer is always the most stable product. Okay? Any questions?
Wait, which one exactly is the thermal product again?
So the thermodynamic product.
Right?
Sorry, what was that?
B, right?
So no, in this example, A is going to be both the kinetic and the thermodynamic. Because,
Okay. Thank you.
no worries.
Wait, no, I'm listening to the explanation. I'm
Oh,
sorry for
okay.
cutting you off.
No, it's okay. Okay. So the thermodynamic product is the one with the lowest potential energy. So since we know A is lower on the graph, that has to have the lowest potential energy. So it's the most stable. And then we know that activation energy being lower means kinetic product. So the one with the smaller hill is going to be the kinetic product.
Okay. Thank you.
You're very welcome. Alrighty, so I'm just going to send you guys the attendance thing again. Pretty please fill it out if you haven't already done so. And yeah, I'll stick around for another minute or two in case anyone has questions or they want to screenshot certain things. Just let me know. But you're free to go. That's all I'm covering for today. And yes, I can definitely go back and let you screenshot. So first we did this. And just let me know when I can move on. Got it? Okay. So you guys told me the answer, but let me just fill it out here for consistency. So thermodynamic product is C and D. Okay, and I will answer your question in 1 second. I'm just gonna scroll over here, let them take their screenshot, and then we can go ahead and answer it. Got it. Okay, cool. Have a great day. I will see you. And I will stick around to answer some questions, but I am turning the recording off, so adios, peoples.